Welcome, everyone. It's nice to see such a big crowd come out for computational thinking. I guess we're at the right conference. Anyway, my name's Irene Lee, as was mentioned, and I'm the PI of a program called Project GUTS, which stands for Growing Up Thinking Scientifically. It's an NSF-funded program under their Academies for Young Scientists program, which was leftover ITEST money, and that program was just funding for one set of programs. Anyway, so I'm located at the Santa Fe Institute in Santa Fe, New Mexico, and I'd like to get a feel for the crowd. I haven't met a lot of people here. So how many of you are middle school teachers or work in middle school? Several. How many are in high school? Lots. Okay. And then how many use modeling and simulation already? Just very few. How about games and game design? And what about robotics? Yeah? Okay, what about other tools you use with kids for computational thinking? What do you use?
What do I use?
Yeah, or what?
I'm actually a writing teacher.
Oh, okay, cool.
And we use, well, obviously all the writing to back up the research and the work that they're doing in the science and math classes.
Okay.
So I'm kind of on the other side of this thing, looking in, trying to attach and see where writing and English fit in.
Fantastic. Anyone else want to mention? Yeah.
A lot of graphics applications.
Okay.
Flash. Things like that. Fireworks.
Okay.
Macromedia.
And back there was someone else.
Logo programming.
Logo. Great. So I know there are other means to introduce students to computational thinking out there, and if I haven't mentioned during this talk what you use, I would really like to hear more about tools and means people are using. Okay, so I draw my experience primarily from two programs, Project GUTS, which I mentioned, and then the Supercomputing Challenge. The Supercomputing Challenge is a 20-year-old program that's been running in New Mexico, engaging kids in computational modeling. And it was started by Los Alamos National Labs. Every year, between 300 and 500 kids joined the program, which ends in a competition where they present their computational models and their research to a panel of scientists and get judged. So those are my two primary projects. I've also just recently been involved with the ITEST. Do you guys know what ITEST is? Innovative Technology Experiences for Students and Teaching, which is a NSF-funded program now in its 7th or 8th year. And there's a white paper group formed to discuss computational thinking and get some ideas out. And these were the partners, the co-authors on the paper. Particularly Joyce Malin-Smith, I want to point out, is the PI of the ITEST LRC at EDC in Boston. And she's the one who kind of pulled this group together. So the thinking we have on thoughts on computational thinking complement what came out of the National Academies recent reports on computational thinking and the Computational Thinking Thought Leaders Project. What we thought we could contribute to what was already out there were examples grounded in programs where we work with youth. Some of the reports coming out of NAS were very much the computer scientist's view or the learning scientist's view. And also the Thought Leaders Conference project, while it was very good, that was sponsored by CSTA and ISTE, it didn't really get down to the level of, well, what do you do in your project and how does that relate to computational thinking? So we felt there was a gap there that we could fill. So in this talk, I hope to cover the following. What is computational thinking? What does computational thinking look like in practice with youth? How can we support growth in computational thinking both in the in-school and the out-of-school arenas? How can we assess computational thinking and the growth of computational thinking in students? And some recommendations we have for next steps. And this is the combined thinking of primarily the white paper group. So, getting down to business, what is computational thinking? I'm sure you've read a lot and heard a lot of different opinions. What we based our paper on was the definition first proposed by Wing, that computational thinking is a set of skills, habits, and approaches integral to solving problems using a computer. Thinking problems that involve systematically and efficiently processing information and tasks. And I guess what's most pertinent is applying these skills and tools to problem solving, okay, to real world problems. That was our interest. There's reasoning at multiple levels of abstraction, there's automation, and attention to dimension or scale. The three pillars were described in a recent article by Cuny, Snyder, and Wing. I'm not sure if it's published yet. It's coming out pretty soon in ACM, CACM? Okay. Thanks, Steve. It's not out yet. But they put the three pillars of CT as abstraction, which is the stripping down of a problem into its most fundamental components, or capturing common characteristics of a group into a smaller set, which can then be used to represent the group. Automation, which is using computers as a labor-saving device to execute tasks, repeatedly and accurately. And to which they added analysis. Analysis wasn't part of their earlier writings in 2006 and 2008, but I think this is very important. It's going back and reflecting on what you did in the abstraction and automation phase, and reflecting, if the abstractions, were the abstractions I made correct? Right? Are they valid? And I think that reflection piece is very, very important. Some other things, so computational thinking primarily emerges from computer science. And we had a lot of discussion within our group about whether kids can do CT without a computer. And yes, there are things like CS Unplugged that teach fundamental computer science concepts very well with manipulatives and games and simulations, full body simulations, and we think those are very powerful, and we don't mean to keep them out of the conversation. We think they're very important. So also another discussion comes up about, well, how do you frame computational thinking? Is it a subset? Is it a superset? So we have algorithmic thinking, mathematical thinking, design thinking, engineering thinking, procedural thinking, and I'm sure there are many more. And for the sake of discussion, we're talking about computational thinking as pieces of all of those, but what's specific is that it's applying those thinking skills to computational media. Does that make sense? Does anyone want to have any other comments on this, or would put it differently?
Bit on applied to computational media, what that means?
Okay, so for example, you're looking to solve problems using a computer, right? So there could be, what's a good example? Recursion. Yeah, you want?
I used to use the MP3s and modify them to change the tempo, change the key of the song.
Right.
Taking the data file and modifying it to do different things to the music.
So what kind of thinking would you put that in before and then after? I mean, does it fit into a procedural thinking that then becomes computational thinking because it's done on the computer?
Right.
Okay. So I would say maybe recursion in mathematics, but when it's applied to certain algorithms that runs a recursive process on the computer, it's an application of that concept to a computational media. Does that make any sense? I'm getting the no look from Phil. Anyone else? Any comments there?
Computational media, would that encompass calculators?
That's a good question.
Sure.
Yeah, why not? I guess would be the question, right? Any other thoughts? So much of what we're doing is somewhat nascent, and we're still thinking it out and very open for other input on different ways of seeing this. And If you have them, please feel free to speak up. Okay, so what does computational thinking look like in practice when you're working with youth? So we have a premise that CT is key to understanding the capacity to define, understand, and solve the problems we faced in the 21st century, and that youth can develop these skills and patterns of thinking through rich computation experiences in which they play the role of designers, creators, and innovators, right? They become the problem solvers. So I hope to provide you with some examples. The evidence we use of students' computational thinking is seen in the way they frame the problems, the way they create the models or the artifacts, and the approaches they take in terms of abstraction, automation, and analysis. So first, these are the programs that the co-authors of the ITEST working paper on CT represent. So you know about me. Jill Denner is with Girl Games Co. and iGame. Fred Martin, UMass Lowell, has a program called iCode. Bob Coulter, Missouri Botanical Gardens, runs a program called Community Science Investigators. And Walt Allen is in Maine with EcoScience Works. So, and again, we're interested in getting other people involved who run programs and hearing what they have to say and how this computational science framework applies to their programs and what they're doing with students. The domains we looked at were primarily modeling and simulation, game design and development, and robotics. We realized that there are others that we didn't include, such as casual gaming, World of Warcraft. You know, it would be very interesting to find out what computational thinking skills are built by playing Warcraft. Augmented reality, like Eric Klopfer's work, and then digital media creation, Digital Youth Network, and also Mark Guziel's work. But we primarily looked at who we had in the working paper group and what we could focus on. So there was no means, no intent to exclude anyone, or this is just the knowledge of the group. So examples of CT in practice. So where does abstraction, automation, and analysis come in when you're doing models and simulation? So we would say an example would be in modeling and simulation, abstraction comes in when you're selecting a real-world problem to incorporate into a model, right? And then perhaps even looking at what pieces of the real-world issue are salient to include in the model. The automation would be the time stepping through the model, as using the model as an experimental test bed. There are also other ways. There's automation in just the looping within the behavior of each agent in the simulation, and so forth. And analysis would be, you know, were the assumptions I made correct, or the abstractions? Does the output of the simulation, does that data reflect any real data set? Okay. Similarly, in robotics, the abstraction task would be to design the robot to react to a set of conditions. You'd have to decide ahead of time what might those conditions be that I'm going to have my robot react to. The program checks sensors and monitors conditions. That would be automation. And for the analysis, are there situations in the real world that I didn't prepare my robot for? Right? Was my model of what the robot's going to encounter in the real world correct? Is another way of thinking about that. And then when we thought about game development, games are abstracted into a series of scenes containing actors, and those actors have behaviors. The game responds to the user's actions generally through a loop looking for user input. And for the analysis, if you designed a game based on the premise that if I added these elements, it would be fun to play, does that hold true? If I give the game to a bunch of friends and they play it, did it have the proper effect? Did I get the effect I wanted to? So that's an element of analysis. Any questions about that? No? Okay. So the domain I know best is modeling and simulation, so I'm going to just kind of talk you through one example. Here on the left, you see a map of, this was the swine flu outbreak recently. I don't know if that's a Google map or not. Anyway, so you have a real world situation, and then you have a student's perception or student trying to relate that to their location or their school. So students know or are concerned in this case about whether swine flu will spread through my school community based on the density of students, the movements of students, how many people were initially infected, and so forth. And maybe they can get some attendance data from that time. So one of the things they would do is they would use abstraction to pick out what they should model or what they think are the important parts. So maybe the color of your backpack doesn't make a difference in the model, but maybe how many different classrooms you're in does, right? Or your movement throughout the day. So we construct a simulation using code and use that as the experimental test bed, run simulations with various variables, what's called a parameter sweep. If you have two variables, you run it across one axis with this set and then across the other axes. So you fill a matrix, and then you do that several times. So kids learn that running a model just once isn't sufficient. There is some randomness in the movement of actors usually, or agents. And these agent-based models are known to be have stochasticity. So whereas you run it once and you get one result, you run it again, you could get a different result. But if you run it 100 times, you'll see a pattern. Maybe 90% of the time, the disease will spread through the entire school, whereas 10% maybe it'll die out. But it gives, so it's not giving absolute predictions. The models give a likelihood of an outcome, okay, and that's important to know. So we introduced this computational science cycle with students, and we use this primarily in high school. In middle school, we don't get all the way around this loop, but I want to tell you about it anyway. Initially, you come in with a real-world problem, and you simplify it into a model or an idea for a model. And can someone tell me, is that abstraction, automation, or abstraction? Right. So you take the real world situation. They even abstract it when they say, let's look at it just within our school community, right? And then you simplify it. And here's where you have more like a mental model or reconception of the real world problem into important elements and how those are interrelated. Next step would be to translate it into a computational model. Is that abstraction, analysis, or automation? Automation? There may be some abstraction in there as well, if they're using data structures or whatnot. And then they would parameterize this model, put in variables to have some different parameters they would sweep, and use it as an experimental test bed and run the simulation many, many times. What would that be? Automation, right? And then finally, they get their conclusions out, and they use those to interpret primarily their model. Okay? And what would that be? Analysis, right. So that's where we see the computational thinking in modeling and simulation. And I think we could do a similar thing for robotics. We could do a similar thing for the game design. But it was helped to lay it out. It helped to lay it out like this and say, okay, right here, this is automation. Okay, so one fundamental point, it's not that kids are just using canned simulations and running them with different inputs and getting outputs. I don't think that's very deep thinking. What we really care about is, making judgments on that model, looking under the hood. How was it implemented? What assumptions were made? Were those assumptions correct? So there's a danger I see now. I saw the NAEP technology standards where they're presenting kids with these simulations And the questions they're asking have to do with, what does this tell you about ecosystems? Well, if you can't inspect that model, I don't think you can say anything about ecosystems, right? So that's often a mistake, or it's a mistake that's tempting to make, that just because it's a CAD simulation, it must tell us something about the real world. Maybe it doesn't. And we want our kids to have that kind of thinking going on. Or else everything looks like a video game and it's a made-up world, right? You need this reflection, and hopefully it drives them to learn more about the code and understand how the code works. So that's where the thinking is. It's not just in running models. It's understanding how they're built, why they're valuable, or if they're valuable. Okay, so some examples from Project GUTS. This was the one I used for the previous walkthrough. These kids wanted to study, transmission of disease, and they modeled the spaceland to look like the layout of their schools with a few mistakes. You'll see there's a room with no doors.
No possibility.
No possibility. Huh?
No disease interaction?
Oh, no, yeah, right. But there was a random seed in there, so, right. Anyway, the idea, and how this is relevant to kids is they study it in context of their school, their community, and that makes it appealing to them and relevant to them. Another one was a study of pollution. We had kids go out with these gas tech meters, and they were taking samples and finding the composition of different pollutants, from cigarette smoke to car exhaust to wood smoke. And then they used some of that data in constructing a model of traffic backing up in front of a school, emitting pollutants. And they wanted to find out in this scenario, how many trees would it take to offset the pollution? Okay? So very much was important to these kids, and something they could model. And it had some elements of, these are middle school kids, had elements of data collection and incorporating that data into the model. There wasn't that last step where they produced data out from the model and said, is this valid? Does this tell us anything about the real world? So that happens more in our high school programs like the Supercomputing Challenge. This is another example where kids from a very, very rural section of New Mexico where there are grass fires came together. Their parents work for the fire department. They were interested in how to design fire breaks to best slow the spread of the fire. And they found out one very interesting thing through their modeling, which is counterintuitive, which is you don't make the fire break perpendicular to the direction of the fire, because that's just the shortest path for the tumbleweeds to go over the road. Actually putting it at an angle was better. And then they shared this with their firefighting community, including their parents and uncles and aunts. And we'll see what the long-term changes. I don't know if it's new research, but it was very, very meaningful for this group of kids, and that really got them bought into it. Okay. So as I mentioned, abstraction's not a monolith. Yes, we say when you go from a real-world problem to a model, you are abstracting it by picking out key elements to model. But there's also abstraction going on, systems being composed of parts, variables. The whole idea of having a virtual test bed is an abstraction of a real test bed. Behaviors of agents. So I think that's something that needs to be clarified in the discussion of computational thinking. I talked to people at an ITEST convening, and one question that came out was, well, by automation, aren't you covering up all the inner workings? Like, are you saying that using a calculator is better than thinking it through because that's an automation? And my answer was, I think you're misunderstanding what we mean by automation. Automation is the automating of processes, but not hiding anything. We're very much into having kids look at the code, really try to understand the the inner workings of models. So automation is not intended to hide anything. Okay? So again, there are multiple levels. I think this needs to be clarified for the general audience to understand computational thinking. And the same for analysis. When you're analyzing a model, there's so many places where you could go, where you can find errors, right? The assumptions you might make, you made at the beginning could be wrong. Key factors could be left out. There could be mathematical errors, programming errors. So again, analysis takes place on many, many levels, and clarifying that would be good. So how can we support growth in computational thinking both in and out of school? We talked about the use of these rich computational tools, not just the simulation that lets you set some knobs and see what comes out, but tools that let you look under the hood, look at the assumptions, look at the coding. Okay? Inspect the assumptions, look under the hood, manipulate the model itself. We think that's very important. The idea of student agency, students as creators and inventors, they have ownership of the project, the investigation, and the creation of the project. It means something to them or their community or their school. That really reinforces the learning and gives them pride in what they're doing. And then using problem-based learning techniques and keeping an interaction going whereby they learn persistence. You know, they're not going to get it right or perfect the first time, and they are going back in and refining their model, getting the output, making judgments. It's this iterative loop, and that's also something that we think is very important. One thing that all of these ITEST working group PIs had in common was this learning trajectory, and we didn't expect this, but we found that the way we introduce both models and simulations, robotics, and game design was through this sequence. So first kids use, for example, the model and run experiments on the model by tweaking sliders, which are variables, through a UI element. Then they go in and modify code, read code, modify it, try to understand how things work. And then later, finally, they get to create their own. And that could be from scratch or making major modifications to an existing program. Okay? And in the create cycle, you get into this loop of test, analyze, refine. So that's not to say it doesn't happen in modify, but one thing I'd like to talk about is you know, how it changes from being not mine when you're just using a model, the sense of ownership, to as you modify it and modify it more, it becomes the student's own work. And we think this progression is good in scaffolding kids' learning and really also understanding about modeling. In the case of the epidemic, you know, use would just be run simulations, using someone else's model, modifying it, and finally creating something that's your own idea. So it has value in engaging youth with progressively more complicated tasks and allowing them increasing ownership of their work. So other people have ideas like this. This is Resnick. He has this cycle of imagine, create, play, share, reflect, and also sees this iterative development is important. And then this is an idea that Alex Reppening at CU Boulder was putting out about keeping kids in this zone of optimal flow between anxiety-producing activities and boredom. Okay, another way we can support growth in computational thinking is to balance out curricular demands. So some of the content for Project GUTS, we have a unit on ecosystems and epidemics, and those fit in nicely with middle school curricula. Another program, the ecoscience work, made a replacement unit for an existing ecosystem unit, and then brought it into the classroom and helped the teacher teach it. Okay, so that's another way. I should say the first one, leveraged content, ecosystems, epidemics, that was done in the out-of-school time. So while kids are learning traditionally about ecosystems in the classroom, they are building models after school. So that's a nice balance. Support investigative learning rather than rote learning, infuse modeling or these other rich tools into existing technology classes. Try to infuse CT across the curriculum. Now, I know people like Maggie Johnson from Google was talking about how, say, in a math class, when you're teaching long division, you can point out to students that you're following an algorithm, just to get them thinking of hearing the words and trying to understand what those words mean. And then, of course, offering CT in the context of computer science classes. Okay. So other issues, accountability was brought up, right? We don't have standardized tests that include CT or address CT. As I mentioned, there's some problems I see with the proposed NAEP tech standards because they aren't allowing kids to look under the hood. It's just use the simulation, what does it tell you about the real world? So it's not even encouraging to think more deeply about modeling, which is unfortunate. And then the recommendation that CT would be better accommodated with accountability or with assessments that allowed for deeper learning and demonstrating their competence through use. Another issue we saw, building teacher capacity. Right, CT isn't offered yet in teacher education programs, and we're asking teachers to do an enormous amount, change their pedagogy, increase their content knowledge, embed advanced technology, understand CT itself, and then sometimes even integrate these field study and data collection in the field to compare it to the data that's coming out of the model. And finally, establish infrastructure. Still some places in New Mexico, there's very uneven access to computers. Teachers don't have time necessarily to teach CT. We need replacement units, which would be helpful, and get administration support. And then how do you talk to parents about CT and get their buy-in? So the 5 programs we looked at are in the after-school time, are offered in the after-school time, and there are many advantages there. The other thing to say is, they're all NSF funded, so definite advantages there. We have the capacity to hire staff and bring them into the after-school period. We provide professional development for the teachers within the school. We don't have the same curricular context as a school day teacher. And then we also have laptop carts and laptops and equipment that we can bring in, MiFis, we can get our own connections going. So it's a special case, and we realize that. Drawbacks of this out of school time, we serve a small group of kids. I mean, for Project GUTS, we served 477 last year, which is pretty good. It's a big program. But you realize how many kids can't come to the after-school time or have a conflict with sports or parents aren't into it, for numerous reasons. So we very much would like to see it more established in the regular school day because of that. Our programs are expensive and grant-funded. It's hard to sustain them. So, okay, I just wanted to talk to you briefly about some of our attempts to assess CT competence. And like I was saying before, this is very early work, but if you have some ideas, let us know. So I was talking to Mark Guzdiel about this work, and he said, well, do you have any proof? Do you have any proof your kids are learning CT? And that's where I think we need to go. These are some early attempts. So one was to study patterns of use, look at the models that students actually create, try to assess those, or score those. We had a user test where kids, well, it was initially set up to be a test of whether the interface of star logo TNG was well designed. So it was initially set up as an adult test. Can you find these blocks? Can you do this? Can you do that? We customized that to make it into a student test where they were timed and had to construct different sequences of blocks to make different procedures. We have pre-post survey data on students' belief about their own efficacy as modelers, as scientific thinkers. And then we have evidence of transference, and those come from interviews. I'll go through each of these in a little more detail. So the first was the idea that we could come up with some kind of rubric or some kind of development trajectory and score models based on a rubric. So we developed this level, set of levels based on the curriculum we taught, and we looked for different levels of sophistication in the students' work. Now, because of the way we teach, where students are using models, modifying models, and then creating unique models, it's very hard to distinguish when they're modifying and when they're creating something that's unique. So for instance, if you have an ecosystem model that has fish in it and there's a set of code for creating and fish giving birth, reproducing later, and them eating, if you copy all of that and just rename it sharks, do you count that? Right? Is that creation or is that modification? There were so many questions we had about how to score these models.
How much time does a teacher take trying to figure out?
Right. Yeah, you don't have the time, right. Nor, it might be a moot point because that really doesn't capture the richness of their experience modeling and making adjustments and testing it and coming back, right?
I think it has to be, it has to be evaluated all the way through. You just don't assess at the end like
right.
you do normally. You have to assess all the way through.
That's right.
And as a teacher, you are sure that this child is doing
right.
not copying.
Right. But then looking at the flow diagram from Csikszentmihalyi and from Repening, that chops the flow into these little pieces for them. So there's some balance, how to do that in a non-invasive way so it doesn't break up their flow of their work, right? Okay, this is data from the time test showing a set of tasks. Let me tell you a little bit about the tasks. Task 1 was find the following blocks: left turn, procedure block, keyboard up arrow block. So they were, keyboard control blocks, the random block, and just drag them out to the desktop. That was the first task. Task 2 is using a run once block or a simple loop. Make the turtle agents move forward, right, forward again. Third one was make your turtle agents walk forever. Fourth was make your turtle agents move forward when you press the up arrow button. Right? So it's a sequence of a series of tasks that build upon each other. And this is for the kids who had completed a year. And as you can see, there's great variability in how long it took them to complete each task. And when compared to the kids who had just attended one summer but not a full year, you could see a vast difference in their completion and timing, right? What they could complete and how long it took them. So that's another maybe proof, right? So when we talk about self-efficacy, I don't know if this is too small to read, but some of the questions that kids rated themselves on are, I am good at coming up with models to make in star logo TNG. I'm good at finding star logo TNG blocks I need to create a program. I know how to add sliders or variables into my program. I know how to make charts and graphs in star logo TNG. I know how to select a real world problem that I can model. I know how to write my own computer models. So these are real self-assessments. And there was a 5-point scale from strongly disagree to disagree, somewhat disagree, agree, and strongly agree. And you can see that there are some, these are the average scores over around 220 kids. And there's some great increases. Like I know how to make charts, graphs, and star logo TNG, adding in a user interface element. You know, that went up almost a point, as did adding sliders. So that was some skill that they came in feeling they didn't know much about, but left feeling they did know about. And then there were 2, I know how to use a computer model to test a hypothesis. That went up 0.43, and I know how to interpret data from computer models. And we compared these to questions, I know how to find information on the internet, which actually went down 0.01. And there was another one, you know, that stayed baseline. So, you know, does this constitute proof? It constitutes self-evaluation, right? So, okay, you'd say to the kid, well, prove it.
Yeah, right.
Yeah, can you build it? Yeah. But
if students evaluated each other, you know, they did a presentation to a partner, and then that student evaluates that, how much they were able to convey what they were
right.
set out to do. If that would perhaps add a little bit more validity.
Yeah, yeah.
I think
Okay.
it also determines the level of the task you give them. You could kill their confidence with a really hard example.
Exactly.
Suddenly they know nothing about that topic.
That's right.
Or you can give them something easy and they think they know everything.
Right. Yes.
I'm curious, it's very clear that the afternoon program can be informed by what happens in school. Have you thought at all about trying to feed it back the other way? Thinking about assessment, of trying to have what they do after school, then turn around and inform what they could do in school. And the reason why I suggest that is if you could do that, let's say in your biology class, you have a natural treatment and control group. The treatment group are the ones who get the afternoon, the control group are the kids who don't.
Right.
You look at the instruction, how the biology instruction, I'm making up biology for example,
Sure.
could change, then you can look at standardized, because there are standardized performance in biology exams.
Right.
And look, A, does the teacher doing this help student performance, and then B, does the students getting this extra school performance? Because now you have normalized exams that states tend to look at. And I don't know how easy that would be to do, how easy it would be to get buy-in from random biology teachers. I'm just thinking about
I think it's not as hard as it could be, because in Project Guts we're lucky. The after-school club leaders are science teachers.
So if you could try and pinpoint that, how to help those teachers to feed it back in, that might give you some very strong evidence that either the use in school or the informing the teachers helps, and or the after-school program really benefits in a way that, I mean, you knock them dead by showing significant changes in biology scores.
Right.
I could see that easily moving on.
Right.
Either direction, either helps the teachers to teach better, and or the students who have this extra exposure can perform better. It might be, not that this stuff is good, but it's going to be hard to take it.
Right.
Whereas if you can actually turn it and feed it back into something that informs school practice, that's much, I would think
that's stronger.
Very, think very strong.
Okay, that sounds good.
That's just a random idea.
But I guess there's some problem in that the kids who come to the after school might be a select group, self-selected group.
But you can pre and post the kids, so you can look at where the students who choose to come in, where are they ranking in the class.
Right.
And you can still look at deltas.
Okay.
So it is somewhat self-selected.
Yeah.
For sure, it's not completely fair.
Right.
But again, you're going to be able to show, and if you pre and post the kids, you know where the kids rank ahead beforehand.
Yeah.
If they're already the top 3 kids, they're probably going to be the top 3 kids when you're done. But if you get kids 1, 2, and 4, and 4 becomes 1, you can see something like that.
Sure. I think that's good.
There are lots of problems with that. have
Absolutely.
the extra time, you have the self-select, you have the extra time on the
Right,
task.
the extra dosage,
So,
right.
That's not a very
It's-
valid test.
Mm-hmm.
But does it buy? If you don't see any improvement, then clearly it shows negatively the kids aren't gaining.
Yeah.
And if it does,
That's it.
But now you can at least make the argument that the kids are doing better. How important is it for the kids to do better?
To learn this way.
Right, to learn this way.
Yeah.
Yeah, because they're going to school better, but it costs us something. Is it worth it to pay for it?
Right, right.
And citizen schools do much of the same stuff. Do they double the contact time, and are they really is it worth it for the extra $10,000 per kid per year?
Right. So the last thing we did was we interviewed kids at the end of their 20 weeks of Project Guts and proposed some scenarios to them without mentioning modeling. It was done after school, but after Project Guts was over. But it's still pretty recent in their heads, I must say. And we didn't mention modeling, and we didn't mention star logo TNG specifically. The two scenarios, the first scenario was there was a fire at the local mall. Your teacher is on a committee that's going to help study how this fire happened and how to prevent such similar fires from happening in the future. Your teacher's asked you to help him or her. Now, there was a reason to make that indirection, so it wasn't the kid dealing with a fire marshal, which might scare a kid. But how would you go about studying the problem and coming up with solutions? That's all we asked the kid. And I think currently at 75% of the kids, yes, modeling and simulation became part of their toolbox of how they would look into this problem. They said they would build a model of the mall. They'd tour the mall to count the doors. You know, they were looking for features of the mall, features of people's behavior that they thought would be good to include in a model. And then they talked about running the model, doing different scenarios. So that was very heartening to see that it wasn't a tool that was tied to just ecosystems, or this is how we study epidemics, but they could transfer its use to new scenarios. The other scenario was water catchment off the roof. Your school wants to get off the city water, and you know, you have designed the catchment system and the cisterns. How do you know when it's safe to get off city water, to turn off city water and make the transition? And how will you know if everyone's needs will be met by the capacity of that system? And again, they were able to talk about it in terms of modeling and parts of the system and inputs and outputs and usage. Again, they didn't create the model, but you could see how they were thinking about the problem and applying these computational tools to help them solve real-world problems. So that's good. Another promising, might be promising, we haven't done it yet, is to do what are called artifact-based interviews. So after a kid has made a model, sitting down with them and talking about the process, what were their goals, what were their findings, you know, try to get a better feeling of that iterative process that kids and their thinking that goes into that. So, you know, again, this is all pretty new, and if you have other ideas on how we might be able to assess learning in CT or what the issues are, be very open to discussing that. And if there are assessment tools used in other fields that might be valid here, that'd be great too. So recommendations for next steps, I'll be quick. Just keep on going in school and out school. We realize that in school is kind of the way it's going to reach the most kids and the fairest way to provide this education. Use rich computational tools that allow for inspection of the assumptions and the underlying mechanisms. And, oops, this latest, there was an ITEST convening trying to come up with research agenda, and there were some specific to computational thinking. You know, what are the learning progressions? How do we assess it? How does it tie with cognitive development? And what might be some design patterns for developing CT lessons? And that's all I have. Does anyone have any comments, feedback, or other ways of doing assessment that might be valid in this context? Yeah.
We're addressing CPU and cognitive development, and the school I work at is specifically for students with mild to moderate learning disabilities.
Mm-hmm.
And one of the things that I've been able to, in the realm of truth, I've been able to take to parents is increase in logic skills, increase in the ability to sequence steps, and the ability to approach and dissect a problem into its basic components.
Mm-hmm.
And those are actually things that logic and mathematics and all of those other subjects have been developing assessments for a very long time. So using logic assessments, that's one way that you can approach some of the cognitive development. And sequencing, those things are something that I would call students have deficits on. And after working on logic, the CT, then I see more generalization.
Okay. Uh-huh.
That's one thing you might work with other teachers on.
Right, right. Okay. Thank you. Uh-huh.
Comment about assessment and how teachers in general don't have a lot of time in trying to do these kind of projects.
Mm-hmm.
For me, any modeling that included a visualization helped to cut my assessment time. For example, if people have used the Carl the Robot stuff, if you have the assessment visually and you can see that it did what it was supposed to do, that really helps with the assessment time. If you have a simulation of a pendulum and it actually swings like a pendulum, you could say, wow, they probably modeled it pretty accurately. You have a grid of numbers and you're playing Sudoku, you can glance and interact and relatively quickly see if they're on the right track.
Okay.
And Steve has this three-dimensional virtual world, and you can look at what the student did and said, wow, they must have modeled it correctly because it looks like it's supposed to look.
Yeah, there's been a fair bit of stuff looking at that. I'd like to get more pushing as a discipline, us validating these instruments more, but I think it's a very insightful to get a sense for doing exactly, Rich, what you're saying.
So a first cut being a visual inspection.
Right.
Okay. Yeah, if your program doesn't run at all, you know.
The infectious disease, the SIR, if you have this table of data, you look at it for a long time, you can't see. If you have a graph of the data,
you can
and
see
you
it.
see the susceptible and the affected and the recovered populations, you can glance and say,
it's like a
wow,
fingerprint. Yeah. Yeah. Anyone else?
Thank you, Irene.
Thank you.